All right, Chapter 1 test for Mod 2. Limit as t approaches 4 of this function. A direct substitution would give us 0 over 0. So to simplify, we would factor the denominator. We know t minus 4 better be a factor of the bottom. These cancel, and a direct substitution would give us 1/5. So you can evaluate a one-sided limit by doing a direct substitution and attempting to find the answer. Limit as x approaches 0. Direct substitution would give us indeterminate form. Because there's a radical, we need to rationalize.
You keep it in the skin? They're not ready. See how they're green? They're not ready.
So on the bottom, don't distribute. Keep it in factored form. So 1 minus, make sure you keep what's underneath the radical in parentheses to distribute that negative. Okay, the 1's cancel, and x from the top will cancel with an x from the bottom. So it becomes the limit as x approaches 0. X over this denominator. A direct substitution would give us 0 over 2, so the limit is 0. And for those of you that took this test, you were discouraged. 0 can be an answer. Alright, limit as x approaches 8 from the right-hand side. If we pick any number bigger than 8 and plug it into this function, say 10, 10 minus 8 is going to be a positive value. So the absolute value isn't going to change the numerator as long as the value of x is bigger than 8. So I can eliminate the absolute value bars. These factors are opposite of each other, so they cancel to -1, and -1 is the limit. Limit as x approaches -6 from the left-hand side. Direct substitution would give us number over 0. When a number over 0 occurs on direct substitution, then we know a vertical asymptote exists, and the one-sided limit will be infinite. So if we pick 5.9, that'll give us a positive value in the numerator and a positive in the denominator as well, so the limit will approach positive infinity. Alright, number 5, this should look familiar, the definition of derivative. So first thing we're going to do, expand the binomial, and then distribute the negatives to both factors. Okay, then we're going to distribute the 2 to the first factor. Alright, now canceling like terms, 2x squared minus 2x squared, x minus x, and then of the remaining terms, each term has a delta x, so we're going to factor that out. Biggest mistake, delta x divided by delta x is 1, so don't lose that term. The delta x's now cancel. Becomes the limit as delta x approaches 0. Making a direct substitution of 0 in for the delta x, we get the limit to be 4x minus 1, which we now know is the derivative of the function. Alright, number 6, limit as x approaches negative infinity of this function. So we did one of these in class, and it is a limit at infinity. So you would want to attempt to use your shortcut rules, but because a trig function is involved, we're going to divide each term by x, which is the highest exponent of the denominator. So limit as x approaches negative infinity, we get 1 all over 2 plus sine x over x. Limit as x approaches negative infinity of 1 is 1, 2 plus, then this is one of our known limits of 0, so the limit of the function is positive 1/2. Alright, now this piecewise function for number 7, you were asked to look at or determine 6 different limits. Part A, the limit as x approaches 0 from the left-hand side. Now, x is a number smaller than 0, so when we plug a negative into this function, it's taking the opposite of the negative, and therefore we can still evaluate the function. So it's not a domain restriction. Direct substitution gives us 0. Limit as x approaches 0 from the right-hand side would be the line. Direct substitution of 0 gives us 3. Because they're not the same value, the limit as x approaches 0 of the function does not exist. Alright, limit as x approaches 3 from the left-hand side. That function is the line, so making a direct substitution gives us a limit of 0. Limit as x approaches 3 from the right-hand side. We now make a direct substitution into the quadratic. That also gives us a value of 0. So the limit as x approaches 3 exists, and it's 0 because the one-sided limits are both 0. Find all values of c such that the function is continuous for all real numbers. Continuity at a point. Function exists. Limit as x approaches a exists. And the last condition, that those y values are equivalent. So we'll focus on the limit because it's the piecewise function. So the limit as x approaches a from the left-hand side would be the quadratic function. Making a direct substitution of a into the function. Then the limit as x approaches a from the right-hand side would be the line. Again, making a direct substitution of a. Now, in order for the limit to exist, we know the one-sided limits have to be equal. So to solve this equation for a, it's a quadratic, so we're going to factor, moving all the terms to the right-hand side. You can guess and check this. This is a perfect square trinomial, so the factors are 2a plus 1 times 2a plus 1. So solving this for a, we get negative 1/2. So negative 1/2 would be the value that makes the function continuous, because we know the only discontinuity would occur where the domain switches. Okay, number 9, sketch this function. Identify x and y intercepts, vertical and horizontal asymptotes. X intercepts occur by finding where y equals 0. Y intercepts occur when x is equal to 0. Vertical asymptotes occur when 0 is on the bottom. Horizontal asymptotes are limits at infinity. So x-intercepts, when you have a rational function is equal to 0 when the numerator is equal to 0. If we attempted to solve that equation, we wouldn't get any x-intercepts. Y-intercepts, we set x to 0, so I get square root of 9 on the top, negative 4 on the bottom, so negative 3/4 would be our y-intercept. Vertical asymptotes, we set the denominator equal to 0, x squared equals 4, so x equals plus or minus 2. Horizontal asymptotes are limits at infinity. When a radical is involved, we have to consider both cases, when x approaches positive infinity and x approaches negative infinity, using the definition of the absolute value. When we use our shortcut, square root of x squared would simplify to x over x squared. Notice this is a bottom-heavy function, so the limit would be 0. And the same would occur when we find the limit as x approaches negative infinity. We would have negative x on the numerator, but still over x squared. Alright, so putting all the pieces together. No x-intercepts. Y-intercept is at -3/4. Horizontal asymptote at 2. Or excuse me, vertical asymptote at 2 and -2. Horizontal asymptote at y is equal to 0, the x-axis. You can use one-sided limits around the vertical asymptotes to verify the direction of the function. And in the middle would be a downward facing parabola. No x-intercepts, only the one y-intercept. Now sketch this function identifying the same information. X-intercepts, set the numerator equal to 0. So x equals 0. Y-intercepts, set x equal to 0. So x and y-intercepts both occur at the origin. Vertical asymptotes occur when the the denominator is 0, setting the bottom to 0. We get vertical asymptotes at positive and -3. And then horizontal asymptotes are our limits at infinity. This function is bottom heavy, so the limit at both positive and negative infinity will be 0, just like the previous problem. X and y intercepts, vertical asymptotes, and again you can use the one-sided limits around positive and -3 to verify the behavior of the function. Okay, that's it.